Great. There we are. Am I on? I hope so. Please, please put things in the chat or in Q&A when you've got questions. This would be good. Haskell Exchange must be one of my favorite meetings of the year, because I love the Haskell community, and usually it's a chance for me to meet many of you in person, and I love that, but not so this time. So I can't see any of you, but I know that you're there in spirit. But it would encourage me if you put things in the chat or the Q&A to make me feel that you really are there, not just having your breakfast and ignoring me. This must be a talk with about the longest words in a single title that I have ever written a paper about. I love the change from provably correct to probably correct. But in fact, we're going to do provably correct. So I hope that by the end of this talk, you will have a sense of what all of these words mean and how they might be true. So I'm going to dive right in there. Please, I really would like you to understand everything that I say. So please, if you don't, start putting comments in the Q&A. I'll watch the Q&A rather than the chat. And you can write comments or questions, and I'll see them right away because I'm watching Hop In as well. And Alison is helping me on the other side. So, but I'm going to dive right in. But I'm going to go fast, and so I really need you to slow me down when you get lost. Please do that. Otherwise, we'll lose touch. I can't even see the whites of your eyes. Okay, so let's see. How can I? Here's the problem. All these machine learning people, what do? They want to design neural networks that recognize cats. What is a neural network? It's some kind of mathematical function, right? It takes in a lot of pixels for the cat, and it takes in a large number of floating point numbers, which are called the weights, and those are the weights for the neurons, and it spits out an output that says how cat-like the picture is. And our goal is to try to adjust the weights so that it outputs, large numbers when you show it cats and small numbers when you show it dogs. That's our goal. Now, in practice, the way we do this is we feed it with a training set. So what's a training set? It's a bunch of cat and dog pictures, or cat and something else pictures. And the cats we label with 1, meaning this is a cat, and the dogs we label with 0, meaning this is not a cat. And we feed it maybe a few dozens or a few hundreds of these, and in each case we take the difference between the output that it says how cat-like it is and the expected output, that is 1 or 0, and that's called the error. And then we're going to add up all those errors, or maybe average them or something. That'll be the loss for this batch of inputs. And our goal is to minimize the loss. So what we're trying to do is to take a pure function. This is purely functional programming, right? This yellow box is simply a pure function. And we want to minimize its output. So it's got the way to think of it is that it's got these 10 to the 8 inputs, right? A large number of floating point inputs, and it's got one real numbered output, and our goal is to minimize that real numbered output. We want to adjust the inputs, that is the weights, until the output is as small as possible. So I hope that is making sense. I don't see any questions here. That's all right. Now, how are we going to do that? Well, if we could imagine that this r to the n thing, that's kind of like a coordinates in space, and you can imagine it's like a topography of a map, right? Hills and mountains, and our goal is to go downhill to get the vertical axis. The height is going to be the output, and the sort of two-dimensional, north, south, and east, west, that's going to be the inputs. And our idea is we want to go in a direction that is going to get us towards as low as possible. So one way to do that is just gradient descent, right? You just go down the direction of greatest slope. Well, what is the direction of greatest slope? We could find that out. Then maybe we could adjust our parameters, right? So P are our parameters, that's our r to the n things. And we could change P by a small factor alpha, let's 0.1 or 0.01 or something, of the direction of greatest slope. So that will move us a bit downhill, and then we'll move it, feed in a whole new batch and get a new output and try to find the director slope and just keep moving downhill, and we'll end up perhaps at a local minimum. So all these gradient descent problems have the possibility of local minimums, but we would just repeat until the slope's nearly 0. And this and choosing alpha and how many iterations you go, this is all black magic, and machine learning people spend all their time trying out different variations. There are lots of variations of this, but all of them need to know the direction of greater slope. So the only message I want you to get from this slide is, I want to find the direction of greater slope for a function that has n inputs, n real numbered inputs, where n is perhaps very large, like 10 to the 8. That's it. That's our goal. If you do that, then you can do machine learning. And after that, it's all, that's a kind of key fundamental component of the whole machine learning world. That's why this gradient descent and automatic differentiation stuff has become so important of late. So how to do that? Well, why my slide's not moving? Here we are. So what is the direction of greater slope? Well, if we knew the derivative of the output, which with respect to the first input, let's just take two inputs, x and y. If we know the derivative of the output with respect to the first input, which is usually in mathematics written as df by dx, right? That's the rate of change of the output with respect to the first input. And if we also knew the rate of change of the output with respect to the second input, then that pair is a little vector. And that vector turns out to be the direction of greater slope, right? It is the gradient of the of this function. So that's what we're going to try to do. We need to know the derivative of this yellow function f with respect to its first input and its second input. That gives us a little vector that tells us which direction to move in to change the parameters to move down towards the bottom. Okay. No questions yet, so I'm hoping this is obvious. It would reassure me if somebody would just ask a sort of token question, so I'm sure I'm seeing any questions that you're asking. Okay, so how do we do this? Well, this is a hot area. There are lots of papers about automatic differentiation, and they are quite hard to read. Some of them are very well written, but they're still quite hard to read. There are some amazing implementations of automatic differentiation that do remarkable things, but I must say I found it quite hard going myself. I've read a lot of these papers and looked at some of these implementations, and they, there's pictures and graphs, and there's lots of examples, and there's derivative traces and perturbation confusions, and there's call with current continuation, and all manner of stuff. But typically, the papers that are good on theory tend to be poor in practice. That is, they may be even asymptotically slow. That is, the program runs in time n, but the implementation, if you directly implemented the paper, would operate in time n squared or something. And the implementations are remarkable, but it's often a bit difficult to understand them because they're not very closely connected to a paper. Right? So the goal of this talk really is to give you a simple principled explanation that will get you from an intuitive understanding of automatic differentiation right through to an efficient implementation. That's my goal, right? I want it to work for reverse derivatives, which I'll tell you a bit more about what that is in a second. I really want it to work for higher order programs. Thank you, Pavel, for a token question. Now I'm sure I can see them. And Alison, thank you. Higher order programs. So we're functional programmers, right? We write higher order functions all the time with lambdas up the wazoo. I want my differentiation mechanism. I want to say df by dx, even though f contains lots of lambdas. I'd like it not just to work for functions of type r to the a to r to the b, but I'd like it to work for some kind of arbitrary types s and t. I'd like it to be fast, and I'd like to be sure that it was right? Because it's awfully easy to mess up. So there's my goal. So how am I going to do it? Well, I'm going to start off with some groundwork on dual numbers. Now, if you've done any reading about automatic differentiation, you sort of yawn at this point. And the dual numbers were invented like 30 or 40 years ago. And that's a good thing, right? It's a simple and good idea. It apparently does not work very well for some of the things I've just described, but if you watch carefully, I'm going to establish notation and we're going to make it work well. So this first bit is kind of old hat, but set in the context of Haskell, and I think my hope is that if you know nothing about automatic differentiation, this will still make sense to you. Okay, so here we go. Given a particular argument of a function x, we want to compute the derivative of f with respect to x, right? That's our goal. So if I've got a function, so the function is on the right of this slide, f with type float to float, and here's a little example function, let y equals x times sine x and then y plus x times 10. So there's a very simple idea called dual numbers, which says let's replace each floating point number with a dual float. And here's the data type declaration for dual. Dual of d is a pair, the data constructor is d, of a float, that's the original float, and little d, right? So this little type d, the d is going to be replaced by different types as we go. And in my initial setup, I'm going to instantiate dual with float prime. What is float prime? It's the derivative of a float. What is the derivative of a float? Just another float. But I'm going to write float prime to remind us that it is actually the derivative. You'll see why this is helpful shortly. So the idea is that the thing I want you to remember about this slide, and it's going to appear a lot in this talk, so concentrate, that is the green box on this slide. Each pair d of y and y prime, whose type is dual float prime, has two components. The y is the float that is the original floating point number that was, in the original computation of f. Right, so it's called the primal. It was what f originally did. So the first component is just going to do ordinary multiplication, division, everything you did before. The second component, which I shall call y prime, is going to be the derivative of the first component with respect to x. That is the original argument to f. Right, so it's always the same x. It's always the original argument to f that I'm taking a derivative with respect to. Right, so the y's will vary. Right, each pair, the second component takes the derivative of the first component with respect to the original x. Okay, let's see, no questions, so I'm hoping that's okay. And I'm just using ordinary old Haskell overloading to make dual float an instance of num, so that f will work just as well over dual float prime actually, as it did over ordinary floats. How is that? Well, I need to make dual float prime an instance of num. So Jan asked, is y equals f of x? Yes, exactly. So that's great. So when I said in the green box, y has kind of is y is type float. Yes, y is always, well, the final y, the dual float that is returned from f, right at in this the yellow box in the bottom left, that dual float prime in the result, the first component of that is indeed f of x. Yes. What does it mean that dual holds the value of f and the value of the derivative at, does it mean dual holds the value of f? Well, Pavel says, does it mean that dual holds the value of f and the value of the derivative at x? Well, only if we're thinking of the result of f. Yes, at the result of f, the dual number is f of x, and the derivative of f with respect to x at x. But of course, all the intermediate values, like this little y in the let clause, that it'll be that's as a sort of intermediate function on the way. Okay, so let's see. So I'm going to make dual an instance of num. How do I do that? Well, I need num of dual of d. So if I add two duals, what do I get? Well, clearly the first component just adds, right? Remember, those are the primals. They do exactly what they did before. We just add them. But what do we do for the question mark bits? Well, remember that the derivative part is the derivative of the first component with respect to the original x. So we just got to remember our elementary calculus. Oops, well, where do we write? Yes, our elementary calculus says if I've got a u and the derivative of u with respect to x is u prime, and I've got a v and the derivative of v with respect to x is v prime, then the derivative of u plus v with respect to x is just the sum of u prime and v prime. So I've got to add u prime and v prime. So I need to do something to these d's, and I'm going to not write it with plus. I'm going to write it with add for reasons that you will see shortly. So add here is going to be a method of a new class called vector space, and add is one of the methods of vector space with type v to v to v. It turns out that for these d guys, I don't need all the operations of num. I only need some very specific ones. So it's going to be this new class vector space. And in fact, the implementation of add, though, on float prime, if I take the instance of vector space on float prime, remember float prime is float, so add is just plus. Okay. So far, so good. So that was easy. What about multiplication? Well, if I'm going to multiply two duals, I've got to, well, the primal component is I just multiply the u and v. And what's the u prime and the v prime? Well, you just look up in your calculus textbook. You say the product rule. What is the product rule? Here it is from Wikipedia. If you want to take the derivative of the product of u and v, you take the derivative of u, all implicitly with respect to some fixed variable x. You take the derivative of u, that is u prime, and multiply it by v and the derivative of v prime and multiply it with derivative v, that is v prime multiplied by u. So I've written this here using scale. So scale takes a float, look at the right-hand side, right-hand blue stuff, takes a float and a v, that is one of these derivative things, and scales it by the float. So we've got to scale u prime by v, and we've got to scale v prime by u, and then we've got to add those two up. With me so far? No more questions? Bit ominous, but there we go. So what I'd like to draw your attention to is how easy this is. All I did is I looked up in Wikipedia and I transliterated into Haskell. That's it. And I can do the same for from integer, because that 10, do you remember that this function had a 10 in it? Yes, there we are. So it's y plus x times 10. That 10 turns into from integer of 10. That's how Haskell overloading works for the num class. So to make dual an instance of num, I need to say what from integer of some integer is. So it's a dual of, well, of course, from integer, that takes the integer to a float. And what's the derivative of a constant with respect to x? Oh, that's easy, it's 0. So I need to have a 0 in this vector space world. So there it is, a method of the vector space class. Okay, still no questions, all a bit ominous. Okay. Now, let me just do one more for illustrative purposes. So this is atan2, which is a method of floating. So I just keep going. I make dual an instance of floating and real frac and all of those classes. Atan2. What have I got to do? Again, atan2 of two duals is well, I take the primal as atan2 of u and v, and then I just look up in Wikipedia, and here it is. So the point I want to make in here is not that. I don't want you to see the details of atan2. I just want you to observe that in the calculation of the derivative, I'm using add and scale, but SU and SV, the scaling factors, they use ordinary floating point operations. Look, I'm doing v squared and I'm doing a division and negation. I don't need any of those in the vector space world. That all happens in computing the scaling factor SU and the scaling factor SV. Okay, so I do some num arithmetic on floats, and then finally I do some adds and scales on the derivatives. So I still only need those vector space operations, even though I'm doing quite complicated things like atan. Edsco says it's just transliteration, but is it obvious why one should be this vector thing that we then scale by a float rather than two values of the same type? Edsco, I suppose it's not entirely obvious. I'm just showing you something that works out. And we're going to see in a while why it's super important that we can restrict what happens in the vector space world. We do not need the full glory, right? So all I'm pointing out is that we can get away with just vector spacing on the second components, because we can do something in the float world and then vector space. So sort of you haven't seen why this is important yet, but it's going to be. I'm just pointing out that it is possible. Okay, thank you. It reassures me that you're there with me. Good. Now then, finally, so now I've got this this overloaded function, num a to a, and I've instantiated dual. I've instantiated num at dual by these instances, but I still need to compute the derivative. How do I compute the derivative? Well, here, this is it. To compute the derivative of this function f, what I need to do is to take a float and return a float prime. That is its derivative at x. It returns the derivative of x. What is the derivative of x? Well, I just need to call f on a dual number. I get back a dual number, and I've got the first component of the result. This is returning to Pavel's question. The first component of the result, r, is indeed f of x, has to be. The second component is the derivative of f with respect to x at x, right? And that is, of course, what I want to return from this function. So this little blue stuff is what I call the wrapper. It takes this dualized f, and it just does a little bit of impedance matching and returns the derivative that we really wanted. So df is the function that we really wanted in the first place. That is a function that computes the derivative of f with respect to x at a particular point. Okay. Now, I had to feed in a dual number. What is the dual number that I had to feed in? Well, of course, I have to feed in x. That's the primal. What is the derivative of x with respect to x? It's just 1, right? So I need that I did with the from integer thing, right? It's the derivative with respect to x is just 1. So it always end up feeding in a 1 in these wrappers. You'll see these 1s showing up quite a bit in the wrapper functions. So I didn't actually have to change f at all. Look, right? I didn't change the code for f one little bit. It's still just the ordinary old Haskell overloaded f. And f could call g. And G could call H, and provided they're all overloaded over nums, I've made no change whatsoever to all the code that I'm differentiating. I've just added this data type for duals, given its instances, and I can compute derivatives for arbitrary functions. Moreover, F and G and H can use arbitrary data structures, lists, they can use recursion, they can use higher order programming, lambdas, anything you like. It's pretty cool. And we can differentiate this stuff. We're done. Of course, it's not really num. If I'm going to do sine, you haven't picked me up on this, but sine isn't in num. So of course, sine is in real float or something. So I'm going to use a slightly more elaborate type class, but that's absolutely fine. I didn't need to do any transformation. And let's see, how fast is it? Well, it takes time linear in the original program. Right, because I just did a few for every multiplication operation. I just did a few more operations, so there's a sort of constant amount of extra work. And I hope that I hope that you're convinced, reasonably convinced, that it does actually differentiate. And it's not very hard to come up with a formal proof that it does. So because it's so simple, it's relatively easy to produce a proof about. Simple things are hard to prove. Difficult things are really hard to prove. So I like simple things. So I'm hoping there's no more questions at the moment, but I'm hoping that you're happy at this point. Of course, this is all old hat. We all knew this 30 years ago. And in fact, but if you're looking for a paper that just fills in some of the details, go and read this paper by Connell Elliott, ICFP. What would this be? 12 years ago. Really nice paper, called Beautiful Differentiation. And Connell in turn was building on early work from Jerzy Karamachuk, and he in turn was building on earlier work. But the nice thing about this paper is it describes not only how to take first derivatives, but how you take the second derivative and the third derivative. In fact, an infinite tower of derivatives. So that second component of the dual, instead of being a single float prime, becomes a pair of float primes, or maybe a pair of float prime and a float double prime, or maybe a triple, or maybe a list, maybe a lazy list of all the derivatives. And Connell's paper is also great for doing, he has a lot of calculational reasoning in it. He has some nice stuff about optimization. He generalizes to other data types. So I do encourage you to look at this paper. I'm not going to cover any of that in this talk. But as so often, I find that talks that I'm giving are basically explaining what Connell Elliott and Ed Kmett have done several years ago. So, but I want to move on to go a bit beyond this real-to-real function. So far I've given you a function with one real input, one real output. What happens if I want to do more? Well, if I want two outputs, that's not so hard, right? I'm going to produce a pair of outputs, float to float, comma float. Here's a little example program. What do? Well, it's not really very difficult. Because I can, everything works completely smoothly. I apply f to dx1 as before. This is the wrapper function again. I just have a new wrapper. I don't have to do anything new, just a new wrapper. And of course, f now returns two dual numbers. And I unpack each of those duals to get r1 prime and r2 prime. And I pair them up, and that's the result of my df. Couldn't be easier. So I'm hoping that at the moment you think you're sort of yawning and thinking, well, that was a bit, why? What's the excitement here? Is everybody happy? I'm hoping. Please ask a question or make a comment if not, because I'm watching. I'm a bit disappointed you haven't. But multiple inputs are a little harder, right? Supposing I've got a function that takes 3 inputs and produces 1 output. Here's a little example. And notice this is the thing that we want, right? Our real functions have 10 to the 8 inputs or 10 to the 9 inputs and 1 output. These are the functions that we care about. So if this doesn't work well, we are stuffed. Well, it doesn't. It works, but not well, as you will see. So here's what we could do. Look, since it takes 3 inputs and produces 1 output, if we call f, what are we going to call it? We've got to call f on 3 dual numbers, right? If we say, if we want the derivative of f with respect to x1. That's one of the things we want, is the derivative of f with respect to the first input, the derivative of f with respect to the second input, the derivative of f with respect to the third input. Those are the three results we want. So concentrate on this first line of the where clause. The derivative of f with respect to the first input, that is x1. What is that? Well, we better apply f to three dual numbers. What is the derivative of x with x1 with respect to x1? Oh, it's 1. What is the derivative of x2 with respect to x1? Oh, it's 0. What is the derivative of x3 with respect to x1? Oh, it's 0. So now I've got three dual numbers I apply f to, and that will give me the derivative of f with respect to x1. And then I can do the same for x2 and the same for x3, and that gives me three separate derivatives, and I can triple them up, and that's my wrapper function. Still no questions. It's profound disappointment to me, guys. So this looks all very well for 3 inputs, but it's not very good if you've got 10 to the 8 inputs, right? Because then you've got to call f 10 to the 8 times, and f might be a big function that calls many functions and does all these folds and maps and so forth. So that is not very cool. But before I sort of go into how to deal with this not coolness, just let me remark that the very same, nothing new or complicated happens if you have functions that take 3 inputs and produce 2. What does this one take? 3 inputs and produce 2 outputs. I can combine the last 2 slides, right, which I had 1 input, many outputs, and many input, 1 output. I can have many inputs, many outputs, and here's, I've written it out in its full glory here. I won't pause very long, except to say, if I have many inputs, many outputs, I need to produce in the output, the wrapper needs to produce an output that has a number for the derivative of each of the outputs with respect to each of the inputs. So I need here 6 outputs. This is called the Jacobian, or the full Jacobian for f. It is, if you like, the full derivative for f. Travis asked me if we're going towards an identity matrix. Those 1 of 0s really look like 1. Kind of. Actually, we will see more. It's an intriguing question. But I think probably the answer is hang on a bit, Travis. But thank you. It reassured me that you're there. Good. So this is the full Jacobian, and we can get it. I'm not going to concentrate any more on multiple inputs, multiple outputs, but I just want to make the point is that all this scales up nicely when that's what I want to do. Okay, so but I want to go back to my problem of not calling f 3 times or 10 to the 8 times, because that would be bad. So my first fix then is going to be to take a tuple of outputs. Now, for the first time, my dual numbers are not going to have a float prime as their second argument. They're going to have in this case, a triple of float primes. So remember over here, what did I do? I called f applied to 3 dual numbers, then I called f applied to 3 dual numbers, then I called f applied to 3 dual numbers. And you can see that the control flow of f never looks at the second components, it just computes with them, right? All the control flow of f is driven by the primal component. If there were any ifs, they would only look at the primal. So f's control flow is driven only by the first component, not by the second component. So a clever idea might be, instead of calling f 3 times, maybe I could take those second components of those dual numbers and tuple them up to make a triple, right? So here it is. So I'll so here and in dx, that dx is going to be, this is the wrapper function again. Dx is going to be the input to f that I'm going to call this time just once. And the second component of each of the duals is now a triple of floats. And in the green box, it gives you the key insight that in the second component of every dual number will be a triple, and each component of the triple will be the derivative of y with respect to xi, right? The ith component of the triple is the derivative of y, the first component, with respect to xi, one of the 3 inputs. So I'm computing the 3 derivatives simultaneously. That's just a standard kind of trick to do, is to tuple things up. So now with that insight, I can see that I have to apply dx comes with a triple, and that tuple is 1, 0, 0. The derivative of x1 with respect to x1, the derivative of x1 with respect to x2, and the derivative of x1 with respect to x3. And then the second component comes with another tuple, the third component comes with another tuple. These are one-hot vectors in effect. Then I call f at a rather more complicated type, right, a dual of tuple of float primes, and I get back what? Well, a tuple of float primes, and that's what I return for r prime. So in order to do this, of course, I need my the second components of my duals to be a vector space. So I need a tuple to be a vector space, and that's really easy to do. I think I haven't even written the instance declaration. I think you can see that if D1, D2, or D3 are vector spaces, then I can easily make D1, D1, D2, D3 into a vector space. Okay. With EDSCO says, with fixed number one, we haven't saved any work yet. Actually, we have EDSCO because in F, we might have computed a really expensive value, a really expensive thing about the primal, right? Like, to decide which way to go. Of course, we are still doing all the work of computing all of the derivatives, but we're not repeating the work of doing the main job of F, if you like. But of course, if we want all the derivatives, we do have to do all the work to compute all the derivatives. We just don't have to repeat all the work of computing the primal. And quite a lot of the primal ends up in the derivatives, and that we want to amortize as well and do only once. Thanks, EDSCO. All right. Now, what's bad about this? Well, we have saved some work, but this type is beginning to look big, right? We've got this dx is now a tuple of things that contain triples. So it looks as if size 9. Oh, my. Actually, EDSCO is maybe right in a way that the work of doing the derivatives looks as if it might be a lot, because after all, if it was not just size 9, but size 10 to the 8, then this could get really bad. So let's first of all switch to arrays, right, or rather vectors. So I'm just going to use vectors, one-dimensional vectors. And here's a little function over one-dimensional vectors. In this particular F, it's a 3-vector, but it can be a vector of arbitrary size, of course. And so here I've just had to recast the wrapper. This is the wrapper function yet again. Here, df is taking a vec float, that is the input to f, and producing a vec float prime, that is the partial derivatives of the function with respect to each of its inputs. So the output vector is the same size as the input vector. And how do we compute it? Well, bottom line, we call f on the bottom line of the blue code. We call f on at dual of vec of float prime instead of a tuple of float primes. We have a vector of them. And on a dx, what is the dx? Well, the dx has to be a vector of these dual numbers, and each of the dual numbers has a vector of float primes inside it. And what is that vector of float primes? Well, it's just it's a vector of one-hots, right? A one-hot is a vector that goes 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. It's got a single point. So it plays exactly the role we had on the previous slide of those 1, 0, 0, 0, 1, 0, 0, 0, 1. So I'm hoping that everybody's happy with one-hot. So one hot is just a standard function that takes the bounds of the vector and a single spot and returns a vector that has a 1 in just that spot. Okay. Are we all good? Oh, and of course, in the green box, as ever, the key idea, y prime is now a vector of the same size as x, the original x, right at the original argument to f, right at the top. In which each element of the vector is the derivative of y, that is the first component of the dual number, with respect to the ith component of the original input to f. Okay? All right. Good. So now we can see in sharp relief what is wrong with this. Right, this is completely infeasible. Right, because now we have 10 to the 8 inputs, and so dx is a vector of size 10 to the 8 of dual numbers, each of which contains a vector of size 10 to the 8, all of which whose elements are 0 except one of them. Right, we cannot, even today's computers do not easily work with vectors of type 10 to the 16. Right, so I'm hoping you're thinking, guys, completely. So this is one reason that dual numbers appear not to scale well to dealing with reverse mode automatic differentiation, which is the reverse mode is when you have lots of inputs and one output. Now, so what are we going to do? What are we going to do? Well, you might think, I hope that you're thinking, guys, just sparse mode, sparse matrices, right? These one hots are mostly zero. So we just turn on standard technology for sparse matrices? And we kind of are going to do that. But standard sparse matrix technology isn't going to work very well for us because the sparse matrices don't stay sparse. We're going to add these one hots together. And after a while, they're going to get fairly dense. And in the end, they're going to be very dense. And if there's anything worse than a 10 to the 8 by 10 to the 8 dense matrix, it's a 10 to the 8 by 10 to the 8 sparse matrix that is mostly full, right? That is even more catastrophically awful. So, nobody asking any more questions. So please, we're now getting to the payload of the talk. So maybe I'll slow down a bit, but I'm hoping that you will slow me down. So what I'm going to do now is show, instead of this vector of floats that we're going to have in our dual numbers, in the green box, there's a dual of vector of float prime. Instead of that vector of float prime, I'm going to have a data structure that is morally the same, that carries the same information, that plays the role of a sparse matrix, and I'm going to call it a delta, right? So delta is going to be a data structure. Here is its entire data type declaration in Haskell. It's a kind of sparse vector representation, and it has four constructors: 0, 1 hot, scale, and add. And you will recognize 0 and scale and add from the methods of the vector space class. Do you remember? And then finally, I'm going to have a function that I said that this delta is a representation of a vec of float prime. Well, if it's a representation of a vec of float prime, we ought to have a function, I'm calling it eval, that given the bounds of the vector of float prime and the delta, coughs up the vector of float prime. So as it were, eval takes a delta and produces a vec float prime. So delta is just another representation for a 10 to the 8 vector of floats. All right, simple enough. Okay. All right, now what? Now, if we just take this representation, what do we do? Just crank the handle. Now my dx, the initial value, is going to be, of course, I must give to f a vector of dual numbers. Because remember, f takes a vector of things. I'm replacing the things, that is these a's, with dual numbers. The dual numbers are now going to be a pair of a float and one of these deltas. So I've got to give to f this dx thing that is a vector of not of floats, but of dual deltas. And how do I get that? Well, I've got to take x, which is a vector of floats, that's the original input. I've got to make an array of pairs in which the first component of the pair is, sorry, array of pairs, that is dual numbers. So that's the d and the dxi one hot. So the first component is just xi, that is the original x from the original ith element of the input vector x, and paired with a one hot delta. Oh, but now one hot of delta, that's just a data constructor of constant size. So now at least dx is only of size 10 to the 8, right? It's a vector of 10 to the 8 pairs of each of constant size. So at least I haven't blown up, on the launch pad. You may worry about what happens when we get off the launch pad, but when we're on the launch pad and just constructing dx, we're only linearly worse than before, okay? Say something, somebody? Okay, so now in order to do this, I need delta to be a vector space, don't I? Well, that's pretty easy because the 0 method of the vector space class can be implemented by the 0 data constructor. The add method is implemented by the add data constructor, and the scale by the scale data constructor. And now that's incredibly easy, right? It fits on a little corner of a slide. But all the stuff about the instances for dual, in vector space, that's completely unchanged. All the calculus stuff, no change whatsoever. No change to f, no change to all the yellow stuff that we had before. The only change is to implement delta and to give it a vector space implementation, which is just the data constructors for it. Okay, so Edsco, I hope I've somewhat answered your question about why I was keen to make vector space into a different class, because now I can see that I only need these three constructors in delta. I do not need, floating point multiply. I do not need sine. I do not need cos. No, no, no. Delta has 0, add, and scale. That's all. Now, but the thing I am sort of hiding under the table. Thank you, Alison. Well, Alison's still here. That's good. But you work for Skills Matter, so you got to. I want a a bona fide, hardcore, balls to the wall Haskell programmer from in production to apply as well. Thank you, but thank you, Alison. Let's see. Right. The other thing I need to tell you about is eval, isn't it? How does sine look like in delta? Sine doesn't. Thank you, Felipe. Sine does not appear in delta. Remember, I'm going to scroll right back to atan 2. I hoped you'd ask this. This is why I put in atan 2. Right, here he is. In atan 2, I had to do exponentiation and division, but I noticed that. Notice that I did those on ordinary floating point numbers. The only things I needed for D were add and scale. Yeah, that's why. Right. So I still do sine and cos and division and exponentiation. They all happen, but all I need to operate on D numbers, the second component of these duals, the derivative numbers, I only need add scale and 0. And that is the sort of amazing insight. It just needs to be a vector space. Okay, so now what about eval? Can you, non-differentiable points, mumble. Doug, I have no idea. Thank you, various people who said we're still here. That's very good. I don't think we need nans. We might need to scale by a nan. What would happen? You need to talk to my colleagues who did the proof of correctness of this. I'm going to pass on that for now. Do I need data constructors, or can you do a final encoding? Oh, Joe, you're way ahead of me. Yes, right. Because what I'm going to do is I'm going to do I'm going to need eval, right? So Joe, let me come back to your question just a second. How does eval work? Well, eval takes a pair, that is the bounds of the vector, and a delta, and it's supposed to produce a vector, right? It manifests the vector in a concrete way. So so what does I need to do? Well, you could imagine that eval could work by allocating a mutable vector and then walking over D. And what does D do? I've got to do some one-hots, which mean add a little thing a particular place. I've got to do some scales, which means sort of multiply up, and I got to do some adds, which just mean, so you can imagine if I've got add delta delta, then I just walk over the first delta, adding them into the mutable results. It's like an accumulating parameter, and walk over the second delta mutating the result. So I can do this with a completely in-place algorithm, super efficient. Scale I can handle by having a sort of handed down parameter that says by what factor I'm scaling. So when I get to a one hot, if I'm currently scaling by 4.3, I add 4.3 into the mutable thing. I haven't given the code for eval, it's in the paper, but it's super efficient, and I hope you can see intuitively it's pretty easy to do. I've got this data structure, and I just walk over the data structure. Now, Joe's question is, whoa, could I have, instead of 0, 1 hot scale and add, if the only thing I'm going to do to delta is to eval it, maybe I could represent the constructors by, what eval does itself, by functions themselves, rather than generating a data structure and later evaling it. And yes, you can, but I think it's easier to think about first. I haven't taken that step in this talk, but it's an excellent point. You're way ahead of me, Joe. Thank you. Now. So at this point, we kind of thought, oh, maybe we're done. But then it became, the people who knew better than me told me, no, Simon, we are totally not done. Here was a not very obvious but super important problem. It is this: if we're calling, supposing we've got this function, let y with some big right-hand side equals something in y plus y. So I'm going to call f at this dual delta thing. So y will also have type dual delta when I evaluate this function at type dual delta. So y will be a dual number with v and v prime, where v prime is a delta and maybe big, right? And what does y plus y do? Well, it takes those, it too produces a dual number, remember? And the dual number that it produces is going to have as its second component add of v prime and v prime. And that's cool. That takes constant time to do. But look, it produces a massive, sorry, it produces something of the right size, but it has a lot of sharing in it. But when we take that data structure and feed it to eval is going to see the first argument to add and walk over it, and the second argument to add and walk over it. It's not going to see, because it's functional programming after all, it's not going to see that those two things are pointer equal and say, oh, I've done that before. It's going to walk over them twice. And this is just catastrophically awful, right? If the function had, was let y1 is something like y2 is y1 plus y1, y3 is y2 plus y2, y100 is y99 plus y99, then a linear sized graph with all this sharing unravels to an exponentially large tree. So eval will take exponential time. Oh, this is, catastrophically awful. What to do? So what we have to do is to make sharing explicit. Let us add to delta explicit sharing. So the two data constructors for var and let are new, right? And they are going to be var is going to takes a delta ID. What is a delta ID? It's just a number. It's just the identity of a a delta ID variable. It's like x, p, q, r, s, y, z, x1, x2, x3. Call them what you like. We'll just call them 1, 2, and 3. Right? Those are the delta IDs. And let is going to effectively, you can think of it as a little language that let binds things. So now add is going to produce this let data structure. So compare. Here I produce add with the pointer to the same thing. Instead, I'm going to produce let with x is this delta ID. The first argument of the let is going to be the big delta. And then the second thing is this add of what? Well, add of not pointers to the big data structure, but add of var x and var x. So I'm just making the sharing explicit in the data structure. And now eval can take advantage of it. Eval can say, I can evaluate the right-hand side of the let just once and use that at both of its occurrences. And in fact, then we can do update in place just as efficiently. We can evaluate these highly shared data structures in linear time. Okay, cool. So this is the insight, right? This is this is what makes the whole thing work. It's kind of, when you think about explicit sharing in a functional language, it's kind of like obvious, the first thing you would think of. The only downside, and it is a downside, is that we can no longer use just type class overloading to do the job. Here is our little function, f of x, you let y equal x times x in y plus y. But I need to convert it this time to a function that is monadic, right? So f subscript d, this transformed version of f, takes a dual delta to an m of dual delta, and m is going to be a monad in which I can allocate fresh delta IDs and in which I can accumulate those let bindings. And of course, each of my little functions like times and plus, they need to become monadic as well. In fact, so this is a transformed f. It's a very straightforward transformation. Completely, if turns into if, lambda turns into lambda, let turns into this sort of monadic form of let. It's all very straightforward. It's in the paper. The operations like plus and times, they of course get changed a little bit. So here is how times gets changed. It takes a dual delta and produces an m of a dual delta. And so it takes, so it does kind of like it did before, but this time it's got to build the sharing. So this delta let thing takes a delta and produces an m of delta ID. So what does that mean? It takes a delta, it let binds it, coughing up a fresh name for it, and returns the fresh name. And the fresh name is what we stuff in the dual number that we return. So every delta in a dual is always going to be small, right? It's always going to be freely duplicable without loss of sharing. So here, plus takes responsibility for doing a delta let and returning a var, right? And I'm going to skip quickly over this slide. It just says, what is this monad? This M monad, I just want to show you, it is really not complicated. It's not some big complicated thing that I'm hiding from you. M, this monad, what does it do? Well, it's just a state monad. And what is the state? Well, it's a state that has a pair of a delta ID, which is the next free delta ID, and a list of bindings, that is delta ID delta pairs. Those are the let bindings that we're accumulating in the monad. So what does delta let do? It just takes the current delta ID 2 and returns that. It bumps it to in the state and adds a new binding to the set of bindings. It's a one-line definition for delta let, and I pretty much told you everything that you need to know about M. So M's a really simple monad. The only downside is that tiresomely we actually do need a source-to-source transformation of our original code, but it's a very simple one. Okay, and what do we have to do to our wrapper finally? I'm going to come back to EDSCO in a sec. What I do in our wrapper? What do I do? I have to, so fd, remember, returns an M thing, so I need to do a run M. What does a run M do? Well, it starts off with an empty set of bindings and a 0 delta ID, and it runs. It does the usual thing with the state monad. It's very simple. It's all purely functional programming, here, and I build this this big delta data structure that I then eval exactly as before, except that eval has to take account of the let. So the wrapper is very simple. Look, there was the wrapper before I did this monadic thing, and here's the wrapper after. See how small it's changed? So f before took a vec a to an a. fd at the top in yellow now takes a vec of dual delta to an m of dual delta, and at the bottom you can see that I need to call run m on fd, and that's it. Okay. Now, so I'm going to come back to you, EDSCO, in a second. I just want to quickly wrap up on this. I've really given you all the payload now. That is the key idea, is this explicit data structure with explicit sharing and eval thing on it. Does it correctly compute derivatives? Yes, it does, and we have a proof of that. So it's simple enough that we can actually have a proof that this thing does the right thing. And this is my colleagues Neil Krishnaswamy and Faustina Kurak at Cambridge Computer Lab. So read the paper, and it'll be in Faustina's thesis as well. Does it work fast? Yes, you can see already that this is fast, right? Every float, the program executes just as before, that every float now turns into d of float delta, and every primop allocates a constant amount of delta stuff, and nothing else allocates delta stuff. So we have this sort of constant slowdown. We may generate a lot of delta stuff, but the amount of delta stuff that we generate is proportional to the runtime of the program. So there is a worry that if the program runs for a long time, you might generate a lot of space. Well, all AD systems have this problem, and there are various things like checkpointing you can do about it. But that's not new. We generate some kind of trace or trail. That delta is kind of like a trace of the execution of the program. In fact, I'm going to show you one. Here it is. Right? If I take the program on the left, I'm not going to look at it in detail, and run it, I get this big squadge of let bindings. The stuff on the right is all the lets that I generated in the delta, and I eval that. And that's so, of course, and I get the amount, the size of the thing on the right is proportional to the runtime of the program. Yes, but that's not new to no. Reverse mode AD always has this property, and there are some compromises you have to make with checkpointing to get around that. So, does it work? Yes. Does it work fast? Yes. Is it new? No. Right. So, as so often, the talks that I give turn out to be just explaining what Ed Kmett did sometime between getting up and having breakfast on a Thursday morning. If you look at Ed's AD library, it does essentially what I've described. And he based this on work by other geniuses, Barak, Pearlmuttter, and Jeffrey Siskind. And you can use this library today. It uses various sort of unsafe, benign side effecty things to do that. Interpreting of the data structure. It's all very cool, actually, to get instead of doing a monadic thing to get the explicit sharing, he does a benign side effecty kind of thing in the style of Andy Gill to get explicit sharing. So yes, one way to think of it is this, you see, that we started on the left and we wanted to get to the right, reverse mode AD, right? But the problem in the middle was all these high order things and so forth. So I have led you through a nice path through green valleys. We have had picnic with beautiful and successful people, and we have walked along paths surrounded with green trees and shadiness, and finished up with reverse mode AD. But Ed Kmett does not do that. he does this. He goes straight through the rock. So that's the Ed Kmett version, and the version that I led you through, I hope you feel has been. But it's nice to know why Ed's library is right, and there it is. So you can now. And I hope you understand it a bit better. Now, so just to wrap up, then. I hope that you think each of these steps was relatively simple. We've just taken dual numbers, and by changing the thing that we paired with the dual number, thing that we paired the primal with, we've got an efficient representation of reverse mode AD. And the nice thing is that we never had to have any issue with lambdas. And I tell you, if you look at reverse mode AD, people have a lot of trouble with lambdas. This approach, which is, again, as I say, is not new in what we're describing. But the dual number story just has no problem with lambdas, which is pretty great, I think. Let's see. There's lots of other stuff in the paper, and indeed stuff that we haven't yet worked out in full detail. More general argument of result types. I want to reassure you that it's totally fine with that. Arrays that have arrays inside them, recursion and recursive types, it's all fine. High order derivatives, yes, I think we can do that in the same way. We want to do something better about representing the deltas and actually build a decent implementation of all this. So I'm going to leave this slide up while I tackle Edsco's question. So Edsco says, did you experiment with high order representation of delta so you don't need to allocate IDs and don't have the possibility of undefined variables, etc.? We didn't, Edsco. I think one of the nice things about this story is it allows us to ask questions like the one you're asking, right? And you can sort of experiment that. In fact, probably tomorrow you could have built something using what we've shown you here that exhibits what you're describing here. I think we could, returning to Joe's earlier question, rather than representing the delta as data structures, we could represent delta as functions. But I think that we'd want them to be functions that did know about. I wouldn't want to represent them just as functions before we had var and let, right? I'd want to represent them as functions once we've got var and let. But I think with the insight of var and let, I think we could go to a more final representation. But I'm not quite sure what you have in mind. You can maybe say a bit more, or even if you're allowed to come on stage, you could tell us about it. But the thing I would like to keep in your mind is, with a setup this simple, you could do these experiments. Any other questions and observations? I'm desperately hoping the answer is yes. Let me just acknowledge my lovely co-authors who did most of the hard work, whose photos are here, and indeed names. Another question on representation. Do you think this would be a good use case for unlifted data types? Well, yes. I mean, delta. There's no need for laziness in this. Right, so we're allocating these deltas, so they might as well be unlifted. Yes. So delta could be an unlifted type, so that we never build any thunks for any of this. Yes, Alex, I do think. I don't think that would make a huge difference, but it would make some. How do we approach verifying the implementation against the proof? Is that done in Haskell or by some other means? So in the proof that you'll see in the paper, here is the paper. You can search for the name and you'll find it very easily. It's going to be in Popple this year. The proof is with respect to essentially an implementation, not exactly in Haskell, but in mathematics. But it's the mathematics that is really close to Haskell, including the monadic stuff. And then the proof is done by a kind of the method of using logical relations. So Faustina and Neil could tell you more about that, and it's in the paper. And if you want to deal with recursion, then you have to crank up a level and use step index logical relations. And at this point, I simply appeal to Neil and Faustina and say, and to Richard, say, guys, go for it. But the proof is given in some detail in the paper, and in much more detail in an appendix to the paper. Anyone else?
Hi, Simon.
Yep.
It looks like that is all the time we have. We are
That's good.
Totally out of time. Thank you so much for your session and for joining us today. And I hope you get to enjoy the remainder of the conference.
Yeah, thank you. It's been a lot of fun. Thank you so much for responding during the talk. It's been good.
Fantastic. See you soon.
Yep. Cheerio.